We have previously discussed the formation of hemiacetals and hemiketals. The reaction could continue on and form an acetal or a ketal. So an acetal is a molecule where we have a carbon bonded to a hydrogen, an R group. And you might remember a hemiacetal has an OR group bonded to that carbonyl carbon. An acetal has the same OR group also bonded to that carbonyl carbon instead of, or it's not a carbonyl in this molecule, but it will have originated as a carbonyl carbon. So the difference between a hemiacetal and a hemiketal is that one of the groups is now an OR group, an alkoxy group, as opposed to an alcohol group. And then a ketal is just about the same, except for that carbon is bonded to two R groups. Remember, these originate from a ketone. Acetals originate from an aldehyde. And then that carbon is bonded to two OR groups. So let's write out that reaction scheme. And in these notes, we'll focus on forming an acetal, but please remember in your minds that the formation is the same for a ketal. We just start with a ketone as opposed to an aldehyde. So let's start with an aldehyde here, propanol. We'll again add ethanol as the solvent, and then this could be again in acidic or basic conditions, reversible reaction. And starting with propanol, adding ethanol, we would have that carbonyl carbon with a 2-carbon chain in addition to that carbonyl carbon. We now have, instead of the carbonyl oxygen, we have that oxygen coming from the alcohol, and then the same thing for the last bond to that carbon. So in this molecule, the OR groups and in the mechanism, we'll see that these come from that alcohol that's added to solutions, or that is the solution. So the alcohol bonds twice to the carbonyl carbon. So let's do the mechanism, and we'll do acid catalyzed again. So if we have ethanol in an acidic environment, the ethanol, just like the previous video, ethanol will be protonated from the acid present Now, both of these molecules, neutral ethanol or neutral alcohol and protonated alcohol, are present when we have the acid catalyzed reaction. So if we're starting with that aldehyde, propanol, we have an acidic environment. First step is carbonyl oxygen getting protonated by that acidic alcohol molecule. So carbonyl oxygen, electrons from that oxygen get protonated. Bond between oxygen and hydrogen will be owned by that oxygen now. Now, I'll warn you here, there are quite a few steps in this mechanism. So let's number all of them. This is our first step, which is a proton transfer step. Our second step, we now have our activated carbonyl Once we've protonated that carbonyl oxygen, remember that makes our carbonyl carbon more susceptible to nucleophilic addition. So that's our next step after protonating the carbonyl oxygen. We do nucleophilic addition. We have neutral solvent and protonated solvent molecules present. The neutral solvent, so the ethanol in this case, is a better nucleophile than protonated. So that's what we're going to add to that carbonyl carbon. Neutral solvent, neutral alcohol creates a bond to carbonyl carbon. Electrons in the pi bond will be owned by oxygen. And this is our step 2, that nucleophilic addition. So just to add names, step 1, protonation of the carbonyl oxygen. Step 2, nucleophilic addition. After this nucleophilic addition step, let's draw the product of this step. So that 3 carbon chain originating from the aldehyde, we now have an OH group where the carbonyl oxygen was. That carbonyl oxygen is now an OH group. And then we have the alcohol bonded to the carbonyl carbon. This alcohol has a positively charged oxygen because now that oxygen has 3 bonds. So our next step is to neutralize that charge through a proton transfer reaction. So step 3, we're going to start working down and then to the left. Step 3 is another proton transfer reaction. In this case, we need to deprotonate that part of the molecule with the positive oxygen. Only other things present in solution are the neutral solvent and protonated solvent. Neutral solvent will be much better at deprotonating. So we'll use a neutral solvent molecule here to deprotonate that positively charged oxygen. And that's our third step. So we draw the product of that step. We have that 3 carbon chain from the aldehyde. Carbonyl oxygen is now an OH group, and we have solvent molecule without the hydrogen bonded to that carbonyl carbon. And all of these steps so far we've seen before. Right here we have our hemiacetal. So in the reaction to form an acetal, the hemiacetal is an intermediate. But this reaction will continue. So our next step, now for you kind of remember what our final product should look like, we should have 2 groups, alkoxy groups from the alcohol bonded to that carbonyl carbon. To achieve that, we have to lose the oxygen that's originated from that carbonyl. So that carbonyl oxygen will actually leave the molecule. Now, in acidic solution, it will not leave simply as an OH, because then it would be an OH minus that gets protonated immediately. That's not going to happen in this acidic environment. So actually what will show and what will happen is that alcohol oxygen will get protonated first by a protonated solvent molecule, and then it will leave. That forms a H2O group, which will be a good leaving group. So we have another proton transfer reaction here from protonated solvent. The oxygen from the OH group will get protonated from the protonated solvent. So here's step 4, another proton transfer. The product of this step is that we now have an OH2 group bonded to what was our carbonyl carbon. This is the carbon where all the magic is happening, all the science is happening at that carbon that was the carbonyl carbon. We have formed this H2O substituent, and this is a good leaving group. When we have a good leaving group, it's probably going to leave the molecule. So the next step, we are now eliminating water. So we are on step 5 now. Step 5, we eliminate water. Now, if we were to just kick off that water molecule from the entire molecule, we'd have an open shell carbon. Well, we all know it's more stable for atoms to be closed shell. So as a water molecule leaves, which is a good leaving group, the oxygen from the new bond to oxygen that was formed from the alcohol bonded to the carbonyl carbon, this will form a double bond to avoid opening the shell of that carbonyl. The second arrow is that I drew towards the bottom of that molecule is really a resonance arrow. That oxygen electron, pair of electrons, we're showing that being shared between oxygen and what would be an open shell carbon. So let's see what we have here now. Now I'm going to kind of, just to align with geometry, shift the angle of the bonds here, because now we'll have a double bond to that oxygen that's part of the alkoxy group. We've eliminated water, so that is eliminated. We have a positively charged oxygen. Well, now look, we have a positively charged oxygen bonded to a carbon. That double bond, it looks like a carbonyl bond. That positive oxygen is pulling electron density away from that carbon. And so now this carbon, again, partial positive charge here, is susceptible to nucleophilic addition. Well, what other nucleophile do we have present? We have our solvent molecule present. Neutral solvent molecule is a good enough nucleophile when we have that positive oxygen bonded to a carbon. So our next step here is another nucleophilic addition reaction. Electrons from the oxygen will create a bond to that partial positive carbon. Electrons from that carbon to oxygen double bond will then be owned by that oxygen. We are on step 6 and we are almost done after this. So step 6 is a nucleophilic addition. Drawing the product of this step, we have that 3 carbon chain from the original aldehyde. We have the alkoxy group, ethoxy in this case, bonded to what was the carbonyl carbon, and a new ethoxy group that is still protonated, bonded to that carbon as well. So we're almost done here. Our last step is to deprotonate that oxygen. So step 7 is a proton transfer. We can use a neutral solvent molecule to remove the hydrogen. Electrons go back to oxygen, and then we have our final acetal product with 2 ethoxy groups bonded to what was our carbonyl carbon, and here's our acetal. Quite a long mechanism here. Trying to zoom out so you can see the entire thing. We have 7 steps. Our first step is activating the carbonyl with protonation from the acid. Second step is nucleophilic addition. We do proton transfer to first neutralize the alcohol that was added to the carbonyl carbon, and then to protonate the alcohol, that the OH group part of that key molecule, to make it a good leaving group. We eliminate water in step 5, which makes the molecule more reactive again towards nucleophilic addition. So we add another nucleophile neutral solvent molecule and then do our last deprotonation to finally get our acetal.